I got to tell you, wow, this has been a morning of tough acts to follow.
I'm so glad you came.
Man, you know, Doro, Therese, and Trish, I didn't sign up for being like this far into the schedule with that kind of opening agenda. So, listen, pleasure to be with all of you. My name is Bob Hariri. I'm a neurosurgeon, actually a neurotrauma surgeon by training, but I just signed up for yoga and dance lessons from Dan. And you know what? Watching him dance, watching all of you dance, I'm taking my jacket off. All right? I know that myself and my colleague Patrick are the things standing between you and lunch. And I noticed a few of you after that exercise are eyeballing the front table. So I'm going to try and move along quickly. And I want to talk to you about some stuff which hopefully will impact everybody's health and wellness for many, many years to come. I spend my life after a career in academic neurosurgery focusing on head and spinal cord injury on trying to deliver new therapies in the form of cellular medicine driven by the remarkable field of genomics so that we can address things that are the barrier to health. Health is defined as the absence of disease. Part of our job for the last 30 years has been to find ways to eradicate causes of premature death, things like cancer and heart disease. But more importantly, we have learned so much in the last 30 years that we are now equipped with tools that have never before existed that will allow us to identify disease before it happens and turn medicine from what has traditionally been a reactive field of expertise into a proactive field of expertise. So one thing that the biotech and biopharmaceutical industry has done over the last 100 years is dramatically enhanced life expectancy. From the discovery of microorganisms that led to disease to the introduction of the first cellular therapy in the form of a blood transfusion to the development of antibiotics to treat those infectious agents to the development of vaccines that help prevent the onset of viral illnesses, to understanding that our biological software that resides in our DNA can be read, and by reading that software, we can understand what the predicted pathway for your life's health will be, to the development of treatments that actually address those underlying genetic causes. We have done a tremendous amount to improve the overall human condition. And we've just embarked in the last several years on a concept that medicine can now become a precision tool to prevent disease and ultimately maintain health. And so, as defined, precision medicine is very dependent on our ability to understand the underlying molecular causes of disease and, when appropriate, be able to act in a preemptive fashion. And this is best evidenced in the paradigm shift which has occurred in medicine, where in the past, practitioners identified disease on the basis of symptoms and on the basis of their experience and their intuition being able to couple an illness to a treatment strategy, to the pattern-based, evidence-based practice medicine which is used today, to what we believe the future holds, which is an algorithm-based, highly precise practice of medicine where we identify an individual's biological propensity for health or disease, address these problems before they happen, and re-steer the natural history of health for that individual. The fact is that so much is happening in the area of molecular analytics and big data management that with the increasing number of therapeutic options available to us, precision medicine will now enable physicians to select those therapies on the basis not just of how they work in a population, but how they can predictably be working in an individual. So this field of genomics, which in many ways had its debut, if you will, upon the first sequence of the human genome by one of my partners, a guy named Craig Venter, the clinical, scientific, and regulatory world recognizes that genomics is now going to become the standard upon which we measure an individual's biological potential for health and identify targets for treatment. You probably know that most cancers today are subjected to intensive molecular analysis, and that analysis allows us to better select agents that work in those diseases, as well as enhance the overall understanding of how specific cancers evolve and potentially identify ways to treat them in a preventative manner. This is being dramatically accelerated by the impact of technology, which allows us to analyze that genome faster and cheaper than ever before. When Craig Venter first sequenced the human genome, it cost $100 million and took 9 months to do. And by the way, he significantly outpaced the predicted time it would take to do that. The NIH anticipated it would take over $3 billion in 10 years to do, and Craig was able to do it in under a year. But that cost was obviously prohibitive as a tool for the practice of medicine. In just a decade, the cost of whole genome sequencing has dropped dramatically. Today, it's under $1,000 to actually analyze those billions of base pairs. And our bioinformatics experts and computational experts are beginning to now unravel what that code means and begins to apply population statistics so we understand what it means to the general population. This dramatically exceeded the predicted decline in cost and increase in speed by Moore's law. So this is actually the revolution in genomics is outpacing even the expansion in computational capabilities predicted by Moore's law. And as you've heard today in some of the earlier discussions, when you couple other forms of molecular analysis, including looking not just at that genetic code, but looking at the derivatives of that code, like the transcriptome and the epigenome, which means that you look not just at the encoded software in the DNA, but you look at the acquired changes chemically that influence that DNA, the epigenome, which, as you heard today, is largely influenced by our daily exposures, many of which occur on the things you're eating every day, like that are on this table. And then our ability to begin to look at how the immune system has an interplay with this, as well as how your metabolism influences all of the activity of that genome, will enable us in the very, very near term to be able to make very, very clear predictions about which way your health is directed and give you a strategy, a roadmap, if you will, in order to change the inevitable to the desirable. One of the things which is serving as an important proof of all this is that you heard about nutrigenomics this morning, which is that everybody's genome can tell us whether or not they will demand a certain type of diet to be healthy and what products they should avoid to be healthy. We're already seeing that genomics can allow us to understand whether an individual will respond to a specific medication or not. Now, as someone who, after my academic surgical career, moved into the pharmaceutical and biotechnological industry, it is somewhat embarrassing to say that if you look across the board, 50% of all prescribed medications today actually don't work in the patients they're prescribed for. Right? What is horrible is look at that failure rate among cancer drugs. Okay? roughly 3/4 of the drugs that are approved and prescribed for the treatment of cancer actually don't have a molecular basis for working in those patients. So to me, it is an absolute moral imperative that we begin to apply these technologies so we can make better choices for our patients. But there's hope on the horizon because a number of important meta trends are influencing how healthcare is evolving right before our very eyes. The advent of reduction in those sequencing costs, those molecular analytic costs, the advent of high performance artificial intelligence and computational tools in the form of machine learning that allows us to address these vastly enormous data sets that are generated by recording people's genomes. To the demand today that all care that is delivered has to be valued, has to deliver true value to the patient and to the healthcare system, as well as the availability of new tools like cellular medicine, like immunotherapeutic products, is having an enormous impact on where I believe all of our healthcare will be in the next 5 to 10 years. And what this means is that by preserving health, by eradicating causes of premature death, we can begin to focus on what's really important, and we've been talking about all day today, which is wellness. You know, I come from a world in medicine where my performance wasn't judged by the wellness of the patients that I treated. It was judged on the basis of their survival, okay? I think everyone in this room agrees survival without wellness may not be worth it, right? Yeah. So the industry, and I've been fortunate to be part of some very interesting players in the field, like Human Longevity, the company that I started with Craig Venter, which is now the largest gene sequencing operation in the world. Believe it or not, we actually showed in the first year of operation, because although intuitively scientists and clinicians recognize how important your genome was, we wanted to show the public how powerful this is. So do you know that in just 1,000 patients' genomes being analyzed, our machine learning experts created an algorithm, okay, a computer program, an app, that actually generated a 3-dimensional rendering of what that person looked like from their genetic code. So if I can tell you what you look like by just looking at your genetic code, you better believe I can tell whether or not you're going to develop a variety of diseases, perhaps even fatty liver disease, obviously cancer. And so as an offshoot of that, as an offshoot of some of the early work I've done in the field of cellular medicine, turning living cells into products that have therapeutic value, we've created another company, Celularity, which is now the leading company turning stem cells and immune cells into medicine. So now, for something a little bit different, I want to shift gears and talk about a field that I know a fair amount about because I spent the last 20 years of my life in it, which is the field of stem cell biology and cellular medicine. And I put this up because several years ago I said, you know, there's going to come a time when we'll be able to accurately say that a stem cell a day will, in fact, allow you to preserve your health. And by the way, that's how nature designed it, okay? All of us are comprised of mature, specialized cells which provide the functionality that is resident in every one of our tissues and organs. But a tiny population in each one of those tissues and organs retains the unique features of stem cells, the ability to mature and differentiate into the highly specialized forms that make up our body. Now, if you think about it, if you've got this reservoir of cells at the ready to fix things, doesn't that suggest that if there's a way of delivering them in a therapeutic way, that it might be valuable as well? So, toward that end, we took a look at the basic biology of stem cells, which is that a single originating cell can give rise to a perfect copy of itself that retains all of that versatility, as well as a very, very specialized, differentiated form of itself, which can go on to become a brain cell or a liver cell. Like Kristen mentioned, the liver is that one organ we know regenerates itself on a regular basis. Well, I'm here to tell you that up until now, we thought that that was a biological process limited, very limited in the body. The truth is, virtually every part of our body has the potential to regenerate itself. In fact, I sometimes say there's potentially the opportunity to unlock your inner salamander. Anybody know why a salamander is interesting, right? Cut a salamander leg off, it grows back. Cut a salamander arm off, grows back. That underlying biologic process to totally renovate and remodel an entire new organ, tissue, extremity actually does reside in human beings at a very finite part of our lifetime. And that finite part of our lifetime happens to be at a time when the software in our biology, in our stem cells, is in its best form. So several years ago, when Craig Venter got the world to begin to recognize that our biological software is a code that's written in the language of DNA, and that code is read by a computational system that resides in the nucleus of our cell, in the cytoplasm of our cells, that if you think about it, every cell in our body is sort of like a small computer, with the software residing in the nucleus, the processor residing in the cytoplasm, the meat of the cell, and the surface of the cell, the membrane, actually behaves like a keyboard. And believe it or not, this actually is how these cells work. A cell can actually detect where it is by a series of keyboard strokes based upon where it takes up residence on the basement membrane of a tissue or an organ. So if I take a bone marrow stem cell from you and I inject it intravenously and it winds up going to your liver, it becomes a liver cell. It doesn't become a bone marrow cell because it reads that underlying software keyboard stroke and it tells the cell which way to go. Now, think about what that means if we can harness that power to turn back on this infinite regenerative potential in our bodies. So many years ago when I was a surgeon, I got a chance to participate, actually observe. I say I participated, but I actually just sat there and watched. Fetal surgery. Fetal surgery is when you identify prenatally that a developing fetus has an underlying abnormality that's amenable to surgical repair. Okay? And you can literally open the womb, expose the fetus, fix the problem, put the fetus back in, and let it develop to full term. And when that baby is born, you know what's amazing? There's no evidence of a scar. Okay? So in spina bifida, where today with prenatal screening methodologies, we can identify that children's spinal cord is exposed, and if they go to full term, that will often lead to catastrophic paralysis and other complications, that if you simply close the skin over that cord, you can actually reinstate the functional endpoint of a normal spinal cord system. And so I thought that was pretty cool to do, but what really impressed me was when the baby was born and we flipped him over, there wasn't any evidence of a surgical repair. Okay? So it got me thinking a long time ago, and a lot of this started, believe it or not, when my oldest daughter was in utero. She happens to be a grad student here at Georgetown. When she was in utero, I got to see this little developing embryo at about 12 weeks gestational age, but the placenta was this giant organ. And when I was in medical school, they taught me that the placenta was a vascular interface between the mother and the developing fetus. If that was true, I'm an engineer, if that was true, they would develop at the same rate. They'd be the same size. But the fact that the placenta was giant size and the embryo was a peanut got me thinking that the placenta must be the rate limiter for the development of that embryo and the development of that fetus. If that's the case, what's it doing? Okay? So this all was taking place at the dawn of stem cells as a science. And if you remember, the first stem cells were isolated and recovered from embryos, which meant you had to take an embryo, destroy it in order to harvest some cells to get started. Now, there's underlying ethical, moral implications about that, but forget about that. Forget about the politics of it, okay? There was something, to me, that seemed wasteful about not looking at other sources that might be better, higher quality, and be much more amenable to the mass production necessary for stem cells to have a meaningful role in medicine. See, for me, as a surgeon who spent time doing transplants and so on, I thought nothing would be more meaningless than for a great technological breakthrough like stem cell biology to go the way of organ transplantation, which is, we know it works, we know it's useful clinically, but it can only be deployed in a tiny fraction of the opportunities that it could be deployed. So I said, someone's going to have to take a living cell, a living stem cell, and productize it. And so we needed a good renewable source of those, and we were fortunate enough to find that in the leftover placenta after a full-term healthy pregnancy. So the stuff that we throw away after childbirth is now known to be the richest source of cells and biological materials for medical purposes. Let me see it. There we go. So what we've learned over the last several years is that the biology of stem cells is unique, but I like to think that every stem cell, regardless of where you get it from, adult bone marrow, peripheral blood, liposuction material. How many of you know that you can actually get stem cells out of liposuction material? What better motivating factor for going and getting a liposuction, right? I strongly advocate that. But every stem cell, regardless of where you get it, thinks it's in a fetus. What does that mean? It means that it's going to try and drive the system. It's going to try and drive the biology back to that state of infinite regenerative potential, like the fetal surgery. Okay? And believe it or not, we're beginning to show that every day. And so I couldn't, as an MD PhD, come up here and not bore you with some graphs, okay? So permit me for a minute just to say that we decided to look at this. And you know what we found? We found that stem cells that reside in this reservoir in all of our organs and tissues declines precipitously. The number of those stem cells decline precipitously as you age. At my company, Celgene, which is a major cancer company, I had the benefit of looking at some data from bone marrow cancer patients and saw that the number of stem cells in bone marrow decreased exponentially with age. Just to put this in perspective, if you bone marrow biopsy a baby, about 1 in 10,000 cells in the bone marrow is a stem cell. If you biopsy the bone marrow of an 80-year-old, it's 1 in 20 million. Okay? Now, I'm not a rocket scientist, although I pretend sometimes to be. The reality is that to me seemed intuitively obvious that the decline in the number of stem cells had something to do with the things that happen to us as we age, right? So, okay, I'd like you to take deep, deep attention to this. All you really need to understand is that I swear to you, we spent a lot of money doing this research. A lot of technicians, a lot of scientists did work. And what we found was that in virtually every compartment of the body, the stem cells responsible for renewing and remodeling those tissues and organs declined with age. Okay, now we know that they're declining, and now we can associate that decline with the accumulation of defects that occur in aging organs and tissues. What can you do about it? Well, I just told you we can find stem cells in the leftover placenta after birth. Turns out there's an entire industry around collecting those cells after birth, processing and storing them. And believe it or not, we've shown that if you give those stem cells back to animals as they age, the animals live 40% longer than if you didn't do that. They're stronger, faster, smarter. So we're now embarking on an entire investigation to connect stem cells to strategies to offset and reverse the acquired defects that we see in all of our organs and tissues as we age. And much of this is related to a very interesting concept. Remember I mentioned to you stem cells are abundant in youth and they decline as you get older? That's simply because those stem cells are being used up to renew, remodel, and regenerate your organs and tissues. It's a perishable supply. And if you look at the ratio between the undifferentiated stem cells to the differentiated specialized cells, that reverses as we age. So if you think about this, we actually have the potential to take when a human being morphs from a youthful form to an aged form, to slow that process down by simply replenishing the cells in those reservoirs that keep us young. The best place that all of you can prove to yourself that this works is go talk to your dermatologist or your plastic surgeon. Tell them you want to have a facial rejuvenating procedure, and they'll tell you one of the best ways to do this is to inject stem cells back into your skin. Like I said, you can get them from liposuction material. You can even get them from blood. Who's heard of the vampire facelift? Anybody heard about that? Okay. What they're actually doing is they're harvesting some of your blood, and they're taking some of the stem cells and some of the factors from stem cells, and they're using that to rejuvenate your skin. And what happens is you're actually restoring the proteins and other molecules that are produced by young, undifferentiated cells that decline as those cells get used up. And we know now that this probably works in multiple systems. We already know it works in muscle. We're beginning to see evidence that it works in the brain. And a big part of what we're doing is working to deploy this to arrest and reverse some of those degenerative diseases that occur with aging. So the process of stem cells going from their undifferentiated, immature, versatile form to the mature, differentiated, specialized form echoes what happens in aging. And it's that reversal in the ratio between these cells, which we now can measure, and we now are developing strategies to deal with. So we believe that stem cells fuel our regenerative engine. And since wellness can best be considered high performance functionality, if function declines with aging, and you can address that with cellular therapy, is that not a way to address some of the wellness concerns we have, right? What constitutes healthy, well aging is the ability to maintain high performance cognitive function, high performance mobility, and yes, youthful aesthetics. Those three things are associated with what we all believe to be healthy wellness. So if you consider the one take-home message that I'd like to leave you with is that aging and the things which rob us of our wellness is likely related to a decline in the number of stem cells that can be used to repair, renew, and renovate us, that this problem has a solution, and the solution is we are literally on the threshold of. Recharging this regenerative engine is something that we're going to be doing with cellular therapy. But believe it or not, you've already heard today about things that we know already impact that pool of stem cells, that reservoir of stem cells. Your nutrition has an enormous impact on this. Exercise, building muscle mass has an enormous impact on this. So you've already been equipped with some of the tools. I'm just trying to give you a sense of what's ahead. So long-term objectives are we're going to use molecular analytics and genomics to understand your diseases, make sure you don't die early. And then, since you're going to live so darn long, we're going to give you stem cells to renew your functionality. So thank you very much. I enjoyed the talk.